Hi, in this tutorial we have an exercise related to acid-base reactions. The exercise asks us write an equation using the curved arrow notation for the acid-base reaction that will take place when each of the following are mixed. If no appreciable acid-base reaction takes place because the equilibrium is unfavorable, you should so indicate. Let's start from the first option. In the first option, we have aqueous sodium hydroxide and a carboxylic acid, which is propionic acid. Let's start writing the equation. Okay, I'm going to write sodium hydroxide as just hydroxide because the reaction is going to take place between the base and the acid. So it is CH3, CH2, COOH. I am writing the carboxylic acid part in detail so that I can show the reaction mechanism. And when we have an acid-base reaction, a base which is hydroxide reacting with acid, so we are forming water and we are forming an acetate ion. You can also write sodium plus with the sodium hydroxide, here acetate minus with the sodium cation. So, but these are spectator ions in the net reaction mechanism, they don't show up. Okay, now like a base is a proton acceptor and an acid is the proton donor. So based on the Bronsted-Lowry acid-base definition, so it's an equilibrium reaction. So what's going to happen? The acid is going to donate its proton. So I'm going to write reaction mechanism like this. A lone pair from the base will go to the a curved arrow starting from the lone pair of the base will end up with the acid's hydrogens. Then we are forming here. So the bond between oxygen and hydrogen in the carboxylic acid should be broken. As you see in the product, we have 3 lone pairs on the oxygen. So the bonding electrons will be on the oxygen. So this is the reaction mechanism. Is this reaction feasible? We have to check the pKa of the acids in both sides of the equilibrium. Here we have a carboxylic acid. If you look at the tables, pKa tables, the pKa of carboxylic acids are like around 4. So it doesn't have to be very precise, but if you check the table, it will give you a value around 4. As you remember, the acetic acid is the famous carboxylic acid. Its pKa is like 4.7 something if you check detail. Here, the acid form is the water. The pKa of water is 15.6. So which one is stronger acid? Acetic acid, sorry, the propionic acid versus the water. The one with the lower pKa is stronger acid. So this is stronger acid and water is weaker acid. Basically, we are looking at acid and conjugate acid in both sides. So reactions like the equilibriums tend to go towards from the stronger acid to the weaker acid side. Yes, this reaction is feasible. Let's look at the second option. The second option says that we have aqueous sodium hydroxide and we have here benzene sulfonic acid. Okay, that's right again. Sodium in the plus and hydroxide. I'm writing detailedly the base, the hydroxide, and this part I'm going to write C6H5. Sulfonic acids are like this. 2 double bonded oxygen, 1 OH. So the acidic proton here is this proton. Let me show with the laser pointer. So this is the acidic proton. Now, what we expect, this is an equilibrium reaction. Let's go back. So this is an equilibrium reaction. So hydroxide is the base. It's electron pair donor or proton acceptor. So when we write the equilibrium, so we should have water as the product plus the benzene sulfonate ion and sodium plus, I'm going to write here. Okay, so this is the reaction mechanism. Base is attacking acid. So base is proton acceptor, acid is proton donor, or based on the Lewis definition, base is electron pair donor. So the curved arrow should start from the electron pair donor from the lone pair and ends up on the hydrogen, the acidic hydrogen, and the bond between the acidic hydrogen and the oxygen should be broken. So this is the reaction mechanism. So is this reaction feasible? Let's look at here. This is the benzene sulfonic acid. So sulfonic acids are similar to sulfuric acid. The pKa is around, if you look at -1, and here water pKa is 16 or 15.6, let's be precise. So we know that benzene sulfonic acid is a stronger acid than water, so the reaction should go from stronger acid to the weaker acid side. So this is a feasible reaction also. Let's look at the option C. We have here sodium ethoxide. I'm going to write CH3, CH2O negatively charged, and sodium is positively charged, reacting with ethyne. Ethyne is an alkyne with 2 carbon. So it's an equilibrium reaction. So one of the hydrogens of ethyne is acidic and sodium ethoxide is basic. So the negatively charged oxygen is basic basically. So it's a Lewis base electron pair donor. So electron pair, we are writing the reaction mechanism starting from the lone pair electrons of oxygen ending with the alkynes acidic hydrogen. Then the bond between hydrogen and carbon will be broken and the bond electrons will be as a lone pair electron on the carbon of the alkyne. So we will have CH3, CH2OH. We are forming ethanol and we are forming the negatively charged alkynes anion. And if you want to write sodium plus also here, because this is negatively charged alkyne, ethyne. Okay, so again, let's look at, is this a feasible reaction? Alkynes, if you look at the pKa tables, generally have a pKa of 25. And we formed an alcohol. And if you look at the pKa of alcohols, it's 16, 17 range. So meaning that ethanol is more acidic and alkyne is less acidic. So basically, this reaction as written in this form is not feasible because the reaction tends to go from more acidic to less acidic side. So the reactant is less acidic and probably sodium ethoxide is also less basic. And also here the alkynes anion is more acidic. So basically this reaction uh, does not uh, tend to go as written this way. So the opposite reaction is feasible, but the forward reaction is not feasible. So let's say that the reaction is not feasible.